radius. Okay, you will see this formula a lot in textbook for design of machine elements. Okay, so it's derived from Mohs circle, right? As you can see, and again, important thing to highlight is no axial load and shear force is ignored. Then you can use this formula. Otherwise, you cannot use this formula at all. Okay? Right. To be frank, this is the easy part. I'll tell you, okay? This is the easy part. Okay? Where it gets complicated is how to determine my, mz, and torque. Okay? Now this is different. Okay, I'll tell you why this is different. This is different because we have to analyze multiple points, moments, and torque. Because we don't know where is the maximum moment. Okay? We don't know where is the maximum torque acting in. Okay, so I'll write this down. Note. Okay. Difficulty is to determine the position where the accumulative my squared plus by mz squared plus by the top square root is maximum. Okay, so I'm going to take you through that process now. Okay, how to determine where the maximum is. Yes. Yep. So we ignore it. Okay. If you have in your shaft design, you have to consider it. You cannot apply this formula. Okay. You can't apply formula. What formula? So you have to do whatever I taught you in week 8. Okay. You have to include your shear force. Okay. Right. So this example over here, we are going to the example now. Anyone questions online, face to face? We are good. Okay. So we are going to look at, you need more time on this page or you're okay? I can see some of you writing. Okay, so we are going to do this example. This is a very innocent example, but it has a lot of stages. I repeat again, this is a very innocent example, but it has a lot of stages. Okay. You can say that this is where the fun begins. Yeah. Okay. You want to make that statement. This is where the fun begins. Yeah. This is a good example. Okay. Example number 1. And I will not be able to finish the example today. Okay. So we need it. Okay. So this is our example. Okay. So we have a motor. Right. You can see over there we have a motor. And I want you to take note. Okay. Note the rotation direction of the motor. Okay, so you have a motor, right? And the motor is driving the shaft AB, right? So shaft AB has a N of 480 RPM, okay, revolution per minute. and it can transmit a power, it can transmit a power from the motor, okay, is equal to 30 times 10 to the power 3 watts. Okay. Then we are given it further information that gear G and H, okay, so if you look at gear G and H, one will take off 20 kilowatt and the other one will take out 10 kilowatt. Okay, so power input is 30 kilowatt on shaft AB. Okay, so we are given that the power output of at gear G is equal to 20 watts, and the power output at H is equal to 10 times 10 to the power 3 watts. Okay. So knowing our shear stress allowable is equal to 50 times 10 to the power 6 Pascal. So this is a material property. Okay. Okay. That is a material property. Determine the smallest diameter of shaft AB. Okay. So this is us. Okay. This is our role. The thing that sometimes put us off is what is this watts doing in a mechanical engineering course? Yes or no? Right? Oh no, right? What are we doing with power? Right? In mechanical engineering courses, it's always stresses, right? So just to make things simple, okay, just to make things simple for us, we know we are going to calculate our shaft. Okay. So the first thing we have to do is to ensure, ensure there is no axial loading, right? So if we were to draw our transformation, this is our X, this is our Y, and this is our Z direction. Okay. So we have to ensure there's no axial load. So i.e. Px must be equal to 0. Okay, and I'm going to sketch our centroid. This is our centroid. By the way, this diagram you can find in your notes last week. Okay, I posted. Okay, I thought it was fun. Okay, and so there is no axial load. So Px is equal to what? 0. Okay, I elaborate on that. Px is equal to 0. Okay. The next thing that we have to also ensure, right? We have to also ensure that the loading condition, right, is just that we have a stress in our x direction, and we just have a torque. Okay, we have to ensure that. Okay, and another thing that we are going to do is we are going to ignore the shear force, the shear stress induced by the shear force. Okay. So the formula we are going to apply is C over J is equal to T Y, not T Y, come on, Eugene. M, so based on this transformation, my squared plus by mz squared plus by tx squared divided by tau max. Okay. Okay. The next thing that is complicated is this. Okay. So I'm going to write number one. Okay. So number one, that I'm going to write the design or analysis or force analysis procedure. Okay, we are going to do the force analysis procedure. Okay, so now let's think about power. So what we are given is power, right? So we are given power input and power output information. So the formula to link power, right, to torque, there's only one. Okay, so y'all will know all this. I think y'all learned this in 2D or even when you're in first year. So power in general is equal to 2 pi n t over 60. Does this look familiar? Right, it does, right? Where n is your number of revolution per minute of the shaft, and T, so this is usually in RPM. T is the torque, and it's in Newton meter, right? So now we have power, right? We have to determine the torque. The thing over here is to determine the torque. Once you determine the torque, we then use another formula. We know torque is equal to force multiplied by what? Radius. Right? We know this also. We know that the torque is equal to force multiplied by what? Multiplied by radius. Okay. So the objective over here is to determine the force. Okay. We are going to determine the force. So when you see this formula, you're like, yeah, this is easy, right? You just plug in a formula. Power is equal to 2 pi nt. Torque is equal to force multiplied by radius. Okay. The thing that is difficult is this. Okay. The difficulty when I put star, this is where the difficulty is to determine the direction of the applied force. Okay. determine the direction of the applied force. Okay. Now, I'm going to draw two circles. Okay, I'm going to draw two circles. And we have to get this right. Because if we don't get this right, we will have problems. Okay, then you say, get what right? So this is one of our gear, right? So this is our driver gear. And I'm going to call this DR. So the driver gear is the input